For Unit 5, Lesson 1, our second last unit in this course, we are going to look at polynomial functions for this unit. More specifically for this lesson, we're looking at identifying polynomial functions. So this shouldn't be new for you. You have seen lots of polynomial functions before, and you know how to identify what is a function and what is not a function. So that is our main learning goal today before we get more specifically into like graphing and stuff in next lessons, okay? So just remember that a relation is a rule describing the relationship between two variables, an independent and a dependent variable. So you could have like something like time and a person's height, or like above ground, or you could have someone's size and their years and age. So an independent and a dependent variable. A function, though, is a relation, so an independent and dependent variable, though, but your criteria here, though, is that it is a relation in which each value of the independent value has one unique value for the corresponding dependent variable. So this is really key, and this is what you're looking at when you're looking at identifying what is a polynomial function and not. So an example here, we'll get into this. This is mapping notation. If you have an independent variable on your left, so remember your independents are your x's, your dependent are y's, okay? If you have that value 16 inputted into this value or this function of g, and the output is +4 and -4, well, 16 doesn't have one unique, right? One unique value, it has two unique. Same with 9. If we input 9 into our function g, and it outputs +3 and -3, well, then it doesn't have one unique value, it has two. So it is not considered a function. Okay, where you're going to see a function is if you input 1 into function f, and it spits out only one dependent variable or one number. 1 spits out 1, 2 spits out 4, 3 spits out 9, 4 spits out 16. That is what is considered a function because each only has one independent, each independent only has one dependent variable. This is another way, which we'll get into, but this is like saying it's the 0.11 or the 0.24, the 0.39, the ordered pair, okay? That is what that map notation is. This would be 16, 4 or 16, -4. This would be 9, 3 or 9, -3. Okay, so we'll get used to that when we actually specifically look at map notation, but there's just a general idea of your difference between a relation and a function, which is super, super important to understand this so you understand the rest of the lesson. Okay, so moving on, it's a little bit of a recap. Just remember that all of the elements that are input into the function make up the domain of that function. So in that previous example, all the things on the left-hand side, so all the things on this left-hand side are independent variable. Those are your x's, okay? All of the elements that are output by the function make up the range. So remember the output is here. That's your dependent variable, which is your range or your y's. So just you have to remember, like this key learning here is that your domain equals your x's. Range equals your y's. Don't mess those up and switch them backwards because you'll get it wrong, okay? And I see that lots, so you need to memorize that your domain is your x's, your range is your y's, okay? So again, here, if we're looking at this function that you saw in the previous slide, your input is going input into the function, so you see the arrow going in, right? So those are your x's, and then your output is your y's because you see the direction of the arrow being output from the function, okay? And the way that you're going to specifically write that is that you just do some of those curly brackets, okay? And then you list the numbers that are your x's. So you would do 1, 2, 3, 4 there because that's the numbers that you see. And then range is 1, 4, 9, 16. Okay, just keep in mind that they need to be listed in order. Okay, so they need to be listed from least to greatest. So when you're doing that, this is given in least to greatest order, which is nice. But they won't always be given, so you'll have to rearrange those numbers. Okay, you'll see a couple examples as we go through the lesson. Okay, so now that we understand what a function is and what the domain and range of a function are, we're going to get into 5 specific ways that functions are represented. So bear with me, this lesson is a little bit longer because we have the 5 different ways that they're represented, but you need to understand what a function is and how you can represent it from these 5 different ways. Okay, so our first way is called a table of values. So we're going to want to write these 5 out, okay, and the examples that are given with them. So here again, you'll see, look, this is an example. They are not written in order, okay? But when you're going to write your x's, so your x's get carried over to your domain, remember that's your x's and your range is your y's, you're going to list them in orders from least to greatest. So 1, 2, 3, 7, okay? And then your range, again, listed in order, 5, 6, 8, 8. However, keep in mind here, it gives it away already, you do not need to write 5, 6, 8, 8, okay? Because it's the same value, we only write it once, okay? So that is important for that when you are stating either a domain or range, okay? However, be careful because not all tables represent functions. So what you're looking for is you're going to, in a table, well, this is kind of every way, but in a table specifically, you're going to look for a repeating x value, okay? So if you see a repeating x value, so here you see 1 and 1, you know that this is not a function because when 1 is input, you don't know whether it's going to be mapped onto -2 or it's going to be mapped onto 5. Okay, so you don't know what the output will be, so therefore it is not a function because you see a repeating x value that has a different y value or a different output. Okay, so I can ask you, is this table of values a function or not a function? And you need to be able to determine that. Okay, so moving on to our second way of describing a function or not is through a set of ordered pairs or ordered points, okay? So what you can do is you can be given a function. So this example, we're given some points, 1, -4, 2, 5, 8, 9, and 0, 6, okay? And when you're given that, all you're going to do is look at the points. Here's your x's. Obviously, they're always on your, remember a point is x comma y. So you're going to list 1, 2, 8, 0, but remember you have to put them in order. So 0, 1, 2, 8, okay? And then the range is your y. So -4, 5, 9, and 6. But again, -4, 5, 6, 9. Make sure you put those in order, okay? So remember, this is your x's, this is your y's. So get used to this as you go through this lesson in your homework, okay? And then this one says, is this set of order pair represented by G equals 1, -3, 2, -3, 3, 0, 2, 0, a function. So again, just look for a repeating, for a repeating x value. And if there is a repeating x value, then you know it's not going to be a function. So 1, nope, we're good with 1s, 2. If there's 3, oh, there's a 2 again. So if you look at 2 and 2, its output would be -3 or it would be 0. So it is not a function, again, because when you have the x value 2, and that's your input, you don't know whether -3 or 0 will be the output, okay? So same as the table of values, you're going to look for a repeating x value, and if you have a repeating x value for that, then your output, you know, is going to be different, and then it is not going to represent a function, okay? Our third way of deciphering, which you kind of saw at the beginning, through what we call map notation or a mapping diagram, is a way to identify a function or not. It's kind of like a table of values, except for a table of values is written, just going to go back here, written directly across, right? So that you read this 1, -2, 3, 4, 1, 5, 2, 7, where for our mapping diagram, you follow the arrows. Okay, so just because 4 is written first doesn't mean it goes with 1. Just because 6 is written first, you'll see here, doesn't mean it goes with -2. 8 doesn't necessarily go with 4, it does in this example, but 2 doesn't go with 3 necessarily. Okay, so you follow the arrows in a mapping diagram to represent your different point. Okay, so here you're going to look at your domain 0, 2, 4, 6, 8. So what they've done here is just taken that domain, which is your x's, they're mapped onto your y's, okay, and put them in order. Same with your range. Looked at it, -2, -1, 1, 3, 4. Put those in order, and those are your domain and range, okay? How you read this is 4 is mapped onto 1. So you follow 4 is mapped onto 1. 6 is mapped onto 3. 8 is mapped onto 4. 2 is mapped onto -2, and 0 is mapped onto -1. Okay, so that's how you read. That's how you read a diagram. Okay, what would mapping diagram look like for a relation that is not a function? So I'm going to draw an example here. So if you had like an example 1, 2, 3. Okay, doesn't always have to be like a round circle around it, okay? And then, so that's your x's, then your y's. Let's go 4, 5, 6, okay? So if your 1 was mapped on to 4, but it's also mapped on to 5, and then let's go 2 is mapped on to 5, and 3 is mapped onto 6. So you can see that 1 is mapped onto both 4 and 5. So it has 2 arrows coming out of it. That is what it would represent, not a function. So your x values can only have 1 arrow. So one arrow, 1 arrow, 1 arrow, 1 arrow. Only ever 1 arrow coming out of them, okay? X's can only have 1 arrow. If more than 1, not a function. Hopefully you can see that on my screen. Okay, so that is a mapping diagram. Here for your fourth way is your graphs. So you would have learned this last year, and you're able to look at a graph and be able to see if it represents a function. So remember that by definition, a function every x value only has 1 value associated with it. So if you look at this, you should be able to look at your x's and look at your y's for each of these. Okay, so if you're looking at this is like, you're going to go over 1, and it's approximately 2, 3, approximately 3.5, whatever. So all your x's, for this example, only have 1 y value because of the way that because it's a line, or because of the way that the line is. So if you were to go over to 1, 2, 3, 4, and you go up and find the value at 4, well, is there any other part of the graph that touches that? No. Okay. Wow, this is not, you cannot see that says 4. Okay. So you're looking for a repeating y value, which it doesn't have. In this example, 1, 2, 3, 4, 5. Okay, so that is x equals 5. Well, at x equals 5, it's going to equal y equals 1, 2, 3, 4, 5, 6, 7, 8, but continues on forever. So in this example, it has lots and lots and lots of y values for its x. So if you input 5 as x, it's going to spit out a ton of y values. So this is not a function. Okay, this is a function. And then for the circle, if you let's go to x equals 1 here. Okay, if you were to go x equals 1, well, it has a y value up here. and it has a y value down here. So it has more than one y value for that x value of 1. So it again is not a function. Okay? The one way that you can use, or one strategy that you should have learned last year, is something called your vertical line test. So if a vertical line, remember vertical is this way, is placed anywhere on top of the graph and it crosses the graph more than once, the graph is not a function because there's more one y value associated with that x value. So again, I'll draw a vertical line, or multiple examples. Bear with me, this should be a straight line. It's not going to be with my little whiteboard, but so if you draw anywhere on your function a straight line, not straight at all there, sorry, but if you draw a straight line here, it only crosses the graph once. What about if you draw a straight line here? It only crosses once. What about up here? Only once. What about here? Only once. Okay, it doesn't cross that x-axis isn't part of your graph. Okay, so it's only crossing once. Right here, right here, right here, right here. Okay, it doesn't matter where you draw the vertical line. If it passes only through once, then it is a function. Okay, if it passes more than once, then it's not a function. This example, you have to draw your vertical line on the graph. Well, this is actually going through like an infinite number of times because you have drawn it and it's touching here, 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 all the way down the graph. So that's why that's not a function. Here's the best example, I would say, for your vertical line test. So draw a line anywhere on your graph. So here I'm going to go through 3 examples. Well, how many times does this vertical line go through the graph? Once here or here. Another line, it goes through once here or here, goes through once here or here. So because it's not a function, because the vertical line test has 2 spots where the line goes through. Okay, so that's kind of how you would describe if you use the vertical line test to tell me if it is a function or not. Okay. Looks like we only had 4 ways to describe a function. Sorry, I should change that at the beginning. So it's only 4 ways to describe if something's a function or not. Okay, so now we're just going to get into more specifically looking at our domain and range. Again, this is something that a lot of people struggle with in grade 11. So again, it's good practice, and you are going to need to understand it for getting into this unit on polynomial functions, because you're going to need to be able to tell me domain and range for those, okay? So remember that real numbers, the set of real numbers is a set of all decimals, positive, negative, and 0, terminating and non-terminating. This statement is expressed mathematically with the set x is an element of the real number system. Or is a set of real numbers, or is a real number. Okay, so there is, sorry, I did not realize that came up on the screen. I thought it was on my next slide. So when you do that, you can either, the way that I just said it is totally fine, or the way that this comes up on the screen, x belongs to the set of real numbers, is totally fine as well. There's no kind of right or wrong for that, okay? Just as long as you know E stands for element or belongs to, and then that R is real numbers, okay? So continuing on, you would have possibly seen this last year, but you have your natural numbers, your whole numbers, your integers that now include negative numbers, your rationals, which are fractions, decimals, which are considered your measuring numbers, transcendental numbers, irrational numbers, those are when you get into roots, and then all of those are considered your real numbers. Okay, imaginary numbers, which you will never look at, but those are your I stands for imaginary, pi I. The square root of a negative number is an imaginary number. We will not get into those. And then your complex. So really what you have to look at is all of this blue here is your real number. So we are looking at any fractions, decimals, roots, negative numbers, positive numbers, zero, anything like that, sine, pi, anything like that is what a real number is. Again, don't copy this out and memorize it. Just have an idea that real numbers are all your numbers other than imaginary numbers. Okay? So when we're looking at our real numbers and stating real numbers, we can list any numbers, but what we're going to do is state our domain and range using real numbers. Okay? So when we do that, we're also going to state if it's a relation, state whether or not the relation is a function. So if you're going to determine if it's a function or not. Okay, so for this first one, your domain. So remember, domain is your x's. And what you're doing when you're looking for domain and range is you're looking for your restrictions. Domain and range. You're looking for restrictions on that graph. Okay, that's your key. So where can your graph not go? Okay, so where can it not go? Where can it not touch is what you're looking for. So for this example, you have a graph that is in your first quadrant and in your third quadrant. And as it goes, it looks like it's getting closer and closer to your y-axis here, and then same here. And then it looks like it's getting closer and closer to your x-axis. Obviously, we can't see how close it's getting because it would be off of our graph, okay, for this picture. But you're looking for a restriction of where you think your x's are never. So let's look specifically at x's. So your x's are going to go -3, -4, -5, and get closer and closer and closer to that x-axis. But I don't think, or it doesn't appear to look like they're ever going to touch that x-axis. And your value of your x-axis is at 0. So you're actually going to have a domain that x cannot be equal to 0, because it is going to get closer and closer to 0, but it's never going to get to equal 0, okay? And that is true for this graph. Same with your range. Look at your y's. Your y's are going to get infinitely close to 0, but they're never going to equal 0. So this is a restriction on your graph. So remember that you are stating x is an element of the real number system, or x belongs to a set of real numbers, such that this line is just like a line, and it means such that x cannot equal 0, and then y is an element of the real number system such that y cannot equal 0. Okay, so that is kind of your notation that you're using. Hopefully this does not look new to you. You would have seen it lots in grade 11. Okay. So we're going to go through lots of examples here. I think I have 4 more examples. Okay. So the second one for B is to state, sorry, I forgot to do this on the last one. So we want to look if it is a function or not using our vertical line test. If we drew a line here, yep, only passes once. If we drew a line here, ooh, it's only passing once, okay? So it is a function, and you would write function because it passes the vertical line test. VLT is totally fine for a vertical line test, okay? So that is kind of your key there. For B, again, state if it's a function, and we're going to state our domain and range. So if you remember from grade 11, possibly not, this open dot means that it cannot equal at that spot. Okay, so more specifically at that spot, this line of y equals 3 is not going to actually touch at x equals 4. Okay, so it's going to get very, 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 very close to it, but it's not actually going to touch at 4. So that allows us to only have one x value, sorry, and one y value at x equals 4 be up here because it actually can't equal right here. It gets really close but doesn't actually equal there. Okay, so if you're going to draw your vertical lines, this would appear that it looks like it touches twice, but it doesn't because it can't equal at that spot. So it actually is going to be a function. Again, a function because it passes that vertical line test. Okay, so your domain here, remember domain is your x's, and you're looking for the value of x's, or the restriction, sorry, of x's. So do your x's, you remember those are left and right, are they ever going to go smaller than 2? No. Okay, but they're going to get bigger than 2. They're going to continue, even though they don't equal 4 here, they equal 4 here, even because they're straight on top of each other. So you're going to continue. Your x's continue to equal something along here all the way to 10. So your x's can only be a value between 2 and 10 on your graph. So your range, or sorry, domain is going to be x is an element of the real number system such that x is greater than or equal to 2, less than or equal to 10. Okay, is how you read it. So read from the middle. Read from the middle. Okay, so again, x is greater than or equal to 2, less than or equal to 10. Okay, that's how you state something like that for that inequality. Okay, the range, again, you're looking at, are there specific values or restrictions that your y's can only be. So for your y's, change my color here, that's up and down. The highest that your y's are going are 4, and the lowest that your y's are going are 1. Is there any values that your y's aren't in between? Okay, so sorry, not 4. This is at 5. Okay, so when your y's are there any values that they aren't? So you're going 5, I keep saying 4. So 5, and then you see values down to 4. You see values down all the way to, like, because these are continuous lines, you see all values all the way down to 1. So 5 and 1. So your range, oh my gosh, losing my words there, is that your y is an element of the real number system such that y is greater than or equal to 1, less than or equal to 5. Okay, so again, this means greater than and equal, and then this is less than and equal. Okay, so that is what you're looking for your range. Okay, so another example, okay, is just ignore this 4. I don't know why that is on the screen. Okay. Oh, I think there may be an error here, but we'll figure that out. Okay, so for each of the following relations, determine the domain and range using real numbers, state whether it's a function or not. Okay, so again, when you're using your vertical line test, go ahead and draw lines on here. Looks like it's a function, looks like it's a function, only passing once. But then you go here, and it passes once, twice. This is not an open dot, so it does, at x equals 4, it does equal 2.5, and it does equal 4.5. Okay, so with that, it cannot be a function because it fails the vertical line test. Okay. Okay, so your example there would be 4 and 2.5, and 4 and 4.5. That's where it fails. Okay, your domain, you're looking for any values, again, for your x's that it can't be. So it can't be less than 2 here. So it can't be less than 2 here, okay? And then it doesn't look like it can be greater than 10 because your graph stops there. Because these are on top of each other, you can still write those, like it appears like the graph is disjointed or it's not connected, but it really is, because at x equals 6.5, it equals in 2 spots, so they kind of connect each other. Okay, so it makes one continuous line technically, even though you don't see it as a continuous line. Okay, so we're going between 2 and we're going between 10, and it can be every value on this line, and this line. So your domain is going to be that it has to be, x has to be greater than or equal to 2, less than or equal to 10. Okay, for your range, I remember now I made a error or a change before we started with that. That's why I put that 4 there. Okay, so the range is going to be the highest that you can go, 4.5. The lowest that you can go is 2.5. But can it be any values in between here? No. Between 4.5 and 2.5, your graph cannot be in between there. You don't see any lines in between there. Okay, so your range is that it can only equal either 2.5 or it can equal 4.5. That's why I had 5.5 before. Okay, so it can only equal 2.5 and 4.5. So when you can only have it equal 2 values, you're just going to separate by a comma. Okay, so again, you're going to see a little bit of a different notation. So you can only have your y's equal at 4.5 and 2.5. So just list them in order. Okay, separated by a comma. Okay, let's look at another example, our last example here. For each of the following relations, determine the domain and range using real numbers. State whether or not it is a relation or a function. So again, it is a function. A parabola is always a function, just because of your vertical line test. So you draw a line here, draw a line here, draw a line here, draw a line here. It's only ever going to pass once, okay? So function, because it passes your vertical line test. Okay, your domain, again, you're looking for your x's. So the lowest that your x's are going are 2. Okay, and then the highest that they go is 9. Okay, so your values have to be between 2 and 9. So you're going to go x is greater than or equal to 2, less than or equal to 9 for that, because it doesn't go like x is 1, x is 0 or anything further this way, and same with this way. Okay, and then same for your y's. For your range, the highest that you go is y equals 8.5, and the lowest it goes is y equals 1, and it can be any value in between because you have all of these values from y equals 3 here, in infinite number of possibilities here, all the way up to a max of 8.5, and then it drops back down. All of these numbers can be in your y values all the way to 1. Okay, so you're going to have a range that's between y is greater than or equal to 1, less than or equal to 8.5. Okay, so get used to this notation and practice it. But you just need to really make sure, key here, that your domain, you remember, is your x's and your range is your y's, and that it's your restrictions from your graphs on those. Okay, and this is where the 5th one came in. I forgot that it came later. On in your on in the lesson for number 5, is how you can tell if an equation represents a function. Okay, so here's your 5th one, last part of our lesson here, is how can you tell if an equation represents a function. Okay, well, you should know that all lines that can be written in the form y equals mx plus b are function. However, which line isn't a function, and what's its equation? So remember, the only line, this is fine. This line here is fine. So that would be like y equals 3. That's fine. A line here would be like y equals -2. That's fine. This is your x and y. Okay, those are fine. So horizontal lines are fine. The lines that aren't fine are your vertical lines at like x equals, let's go -1 here. Okay, so what line isn't a function? It's horizontal lines. Okay, because they, remember, those have that infinite, so at x equals -1, well, it could be y equals 1, it could be y equals 2, it could be y equals 3, it could be y equals 4, it could be y equals 8.5, it could be a y equals 100.5. So it continues on and has lots of outputs of y, so it can't be a function. Okay, so your equation will be x equals a number, whatever that number is, 1, -1, e.g. x equals -1. Sorry, this should be -1. Okay, so that's your example there. That's the only one that can't be a function for a straight line. Okay, all of your other straight lines, even if you drew a line here, this way, yep, that works. If you drew a line like this way, yep, that would work. It'd pass your vertical line test. Okay. Another thing to remember is all parabolas. Sorry, I'm gonna write this underneath it. I didn't realize that was so close. ax squared plus bx plus c. That's what it says under that red. Okay, so all parabolas that can be written in the form y equals ax squared plus bx plus c are functions. What might a parabola look like if it's not a function? The only way that it is not a function, so your parabola here, like this is a function, this is a function, this is a function, so up and down. The only way that it is not a function is if it's turned to the left or the right. So if you see a parabola like this, or a parabola like this, or it could be like up here, whatever, okay? It doesn't matter where it is on your graph. So if you see ones that are sideways, those ones are the ones that represent not a function. You won't see those too much, but you might see them being able to represent if they're a function or not, okay? And then if you aren't sure about an equation, you can graph it and use the vertical line test. So that's kind of key there. And even if you have like access to Desmos graphing calculator, just type it in and you can see if it's a function or not. Okay. And then you can explain why. However, we are going to get into more polynomial functions in this unit. So you'll start to see what some of those equations look like. Okay. So what I'm going to want you to do, oh, sorry, one more slide before I'm going to send you off to do something. If an equation is a function, it will often have a function name. It will be written in function notation. So this is a line. So this is y equals mx plus b. It would be renamed f at x. So it's just meaning that that f of x, which means that the function name f, so your function name f depends on the value of the variable x. Okay, so that is all that function notation is. We say f of x when we say it, or f at x. Okay, it just means that what is that function when the x value is like 1. Okay, and then just a reminder, degree of term for a power with one variable. The degree is the variable's exponent. When there's more than one variable, the degree is the sum of the exponents of the powers of the variables. So here, x is 4, x4, x3y, and x2, y2 all have degree 4. Okay, so because you are going to add x4 is just x4, x3, y would have a 1 there, so 3 plus 4, or 3 plus 1 is 4, and then 2 plus 2 is 4, okay? But that's just degree of a term, okay? So don't worry too much about that. That's just a little extra hint there, okay? So this is what I'm going to do, is to send you off for this lesson, and I'm actually going to get you to submit this to me, so you might have to copy these out if you aren't able to like screenshot this. Try your best for 7, 8, 9, 10, 11, 12. Don't have to copy out the graphs. Just tell me if they're a function or not and why. Okay. And then I prefer you copy out 1 to 6 because it's easy to copy out, and tell me if it's a function or not. Kind of like circle, if it's not a function, circle why it's the points that make it not a function or whatnot. Okay. So I'm going to get you to do that. And then you're going to submit it, and we will take it up. I'll get you to submit on Google Classroom. Okay, I'll advise you more of that on Google Classroom. I'll advise you more of that through like your daily slides or whatnot, or through our sync lesson, okay? Then identify whether each of the following, this is our last slide, where either of the following functions is a polynomial function. If it is not a polynomial function, state the type of function that it is, okay? So anything that is a polynomial function is going to be like something like your linear, oh my gosh, your quadratic, there you go, that it has x and it has some sort of exponent in it. So x squared, or you see 1x to the 1, x cubed would be 1, okay? What's not going to be a function we'll get, or polynomial function, we'll explain here, okay? So because you see x and you see a 2 here, you know that it is quadratic, and it's a polynomial function of degree 2, okay? So it's a quadratic. This is kind of leading us into our next lessons, okay? 3, and then you see the exponent is x plus 2, but because your exponent is an x, it's not a number 1, 2, 3, 4, etc. It is not a polynomial function, it's an exponential function, since the base is a number and the exponent is a variable. So key there is the exponent is a variable, okay? Here, you have f of x equals 4, so this is a polynomial function of degree 0, or a constant function, okay? What about sine 2x? Nope, not a polynomial function. It's a sinusoidal function. You should just recognize that. We just did a unit 2 on that. Okay, again, here, x to the exponent 1. So you see that you can write it as a 1. So it is going to be a polynomial function of degree 1. Here, this is not a polynomial function. It is a square root function. So just keep in mind here, because you see the square root, you probably haven't seen too much of these, but because you see the square root, it's called a square root function. This one again, look, so sine here, it's a sinusoidal function. Cosine is also a sinusoidal function, so it's not a polynomial function. And then 1 all over x squared minus 3 is not a polynomial function, it's a rational function. So because it's in a fraction form, it is called a rational function, so it's not a polynomial. Okay, so that's just kind of getting you into identifying if it's a polynomial function or not. And gets you kind of thinking about what polynomial functions are, because that's our unit for this, okay? So I do apologize, this was a long lesson. Your homework shouldn't be too bad. It is page 82, number 1 to 8, okay? But this is a really key background for understanding what a function is and not is, and then how to identify them throughout this unit, okay? Good luck. Let me know if you have any questions.